So today we're going to be finishing up the gas laws. Finishing up is in the fact of just kind of introducing the different ones. We'll still go over Henry's Law on next lecture, and this lecture is going to be followed by homework. I also have some videos. I have two video clips, one or two. I'm trying to remember now. I tried to do, oh yeah, I'm going to add another one. I might actually wait and add that one for next Friday. Sorry, I'm just thinking out loud. So today is, which I often do in class. So this is for Monday, June 1st, and then I think that other video link that I'll give you. So I'm creating a discussion board. So you're going to be watching the marshmallow experiment. It does unfortunately tell you what gas law it is, but I just want you just to kind of comment on it. So I want to make sure that you've watched it and give me a little feedback what your takeaway was. And then the gas law homework is, I'm not going to have it due until the following Monday. So you're going to have an extra couple of days, so it won't be due until June 8th. It's a lot of math, of course, and I need you to make sure that you're setting up the problems correctly, and you may use your calculator because you're going to have numbers in the 100,000s, and I don't expect you to. It's going to be a lot. So go ahead and use your calculator on it. And we'll probably have a Zoom sometime this week too to kind of go over some problems. Okay, enough of that. Moving on. So the concepts are fairly easy, I feel. They're pretty easy as far as whether they're directly proportional or indirectly proportional, and you'll kind of see this as we go on. There's little video clips for each gas law also to kind of demonstrate it, talk a little bit more about it, which I hope helps. You actually can find a fair amount of problems online too, but we'll just move forward here with Charles' law. So Charles' law is looking at how temperature and volume influence each other. Okay, so what we're saying here is these variables are directly proportional to each other. Okay, so what's varying here is temperature and volume, but what remains constant is your mass and pressure. So those are not going to change. Okay, so as far as how they influence each other, so as the temperature increases, what do you think is going to happen to volume? So you think about it as temperature increases, usually you're heating up the molecules. Okay, the molecules are moving around, they're bumping into each other, so you're going to have an increase in volume. Okay, so these are directly proportional, or they're directly related. Okay, as things cool, then the volume decreases. So kind of think about one thing, if you can make a relationship to it that might help you remember Charles' law is think about when it gets really cold out really fast. I don't know about your cars, but I know my daughter's Volkswagen is really sensitive on the temperature gauge. So when we have those really extreme drops in temperatures, or it drops like 30-40 degrees, so the volume in her tires have gone down. Okay, so the tires then shrink in cold temperature. Okay, so cold temperature shrinks the volume. Okay, another thing is thinking about volume, of course, and then it's kind of related to pressure too, but I don't want to go there right now. I'm just thinking about like how concrete too can bust when it's really hot. So increased volume, increased temperature, decreased temperature, decreased volume. Right, don't want to say any more, otherwise I'll confuse you. So here's like just a little analogy. So you have your K is your constant there. So volume over temperature, as you can see, as you're increasing the temperature, so as you're going along on your x-axis to your right along the temperature, your volume is also going up correspondingly. All right. As known as the law of volumes. So a gas law that describes how they tend to expand when they are heated. So Charles' law then states that the volume of an ideal gas at a constant pressure is directly proportional to the absolute temperature. So if you click on this video link, this is actually a Khan Academy, which are usually really good. So again, as your temperature increases, your volume increases. So it's about an 8-minute long video, but it's a good informative one. All right, now we're moving on to Gay-Lussac's law. Not sure why there's nothing typed here. I hope I didn't. Oh, there we go. Scared me for a moment. So we've got, because I just looked at all this. When did I hit delete accidentally? So here we're looking at pressure and temperature. Okay, so those are our variables. Those are the things that are going to vary. And our constant here is mass and volume. All right. So again, these are directly proportional. As the temperature goes up, the pressure goes up. As the temperature goes down, the pressure goes down. So you can think about a propane cylinder that's filled with volume. As the temperature goes up, the pressure rises, okay, and then it kind of dumps off that pressure with a relief valve. Okay, that's one different analogy to think about. So it's the same, it works on the same principle as far as one going up, the other one goes up. But Gay-Lussac's has to do with pressure, not volume like Charles does. Alright, and again you can kind of see here, we have the constant, so and this is involving pressure and temperature. And there's also a little short video link. Socratic, it's about 6 minutes, a little bit less. So hopefully that'll help. Now moving on to combined gas law. Okay, so this is where we take the different variables of pressure, volume, and temperature. Okay, so we're looking at Boyle's, Charles, and Gay-Lussac's all together. So this one is inversely proportional. So if the volume goes up, the pressure is going to go down. Because think about it, if you have more volume with this law, if you have more volume, your pressure, you have more space for everything to move around. Okay, that's kind of how I think about it. I think of things that are expanding, I have more space for the particles to move around, so it's creating less pressure. However, the pressure, though, is directly proportional to the temperature. So if you increase the temperature, you're going to increase the pressure. All right. So moving on. So this is kind of giving you a little idea, kind of showing you how all the combined gas laws are together. Okay, so we're taking pressure times volume divided by temperature with the constant. That would be your combined gas law. This again is also a tutorial. This gives you some examples of gas law problems, and this is about a 7-minute one, and it's pretty helpful too. So I'm actually, so here's just kind of a little review of what we're looking at. We have Boyle's law having to do with temperature being constant and your volume varies inversely proportional with your pressure. Okay, so another way of writing Boyle's then is P1 V1 equals P2 V2. And one of my students taught me this little acronym, that BAT, B-A-T, BAT. So B for Boyle's and then temperature. So the temperature is constant. I don't know. It can be a little confusing, I guess, if you want that little acronym or not. Charles' law then would be V1 over T1 equals V2 equals T over T2, and that would be CAP, C-A-P, where you have C for Charles and then P where your pressure is constant. So then you're just dealing with your volume and your temperature. So I guess if you look back up at the Boyle's one and you say BAT, temperature being constant, so then you know it's volume and pressure, okay? And knowing that they're inversely proportional. Again, then with Charles' law, with the V over the T1 and the V2 over the T2, your pressure is constant and your temperature and your volume are directly proportional. And I did provide you just like a little grid, a little table that you can fill out, and you can put all this information in there to kind of help you study. And then Gay-Lussac's law, that student told me GLOVE, G-L-O-V-E, where GL obviously being for Gay-Lussac's, and then the volume is what is constant there, and then you're looking at pressure and temperature, and they are directly proportional, okay? And then we have, so that would be the P1 over the T1 equals the P2 over the T2, and then combined gas laws is taking all three of those different variables. And again, K here meaning constant. Alright, so I went ahead and included a little practice problem for you. And you may see this again, hint, hint, on something that's coming up. So you're looking at a balloon that has 106 liters in it when the temperature is 45 degrees and the pressure is 740. Then it's asking what would the volume then be if you decrease the temperature to 20 degrees and the pressure went to 780. Okay, so this is a combined gas law problem. So you're going to go ahead, and the first thing you need to remember to do with these problems is to convert your degrees, your Celsius degrees, to Kelvin. So that's your very first step that you need to do. So your 45 degrees then is going to turn into 318. Remember, taking your 273 plus the 45, that's how you're converting from Celsius to Kelvin. Okay, so your 45 degrees Celsius is now 318 degrees Kelvin. Oops, I think I forgot to put my K there. And then 20 degrees Celsius then for the second part of the problem is going to be 293 degrees Kelvin. Again, just adding 273. Alright, so I did my best. I guess I'm trying to type this out because you know how long it takes forever in a day for me to write it. So you're going to be working with big numbers. That's why I said it's okay to go ahead and use your calculator, especially on your homework, but you need to set them up correctly. So if we're looking at the P1 V1 over T1 equals P2 times V2 equals T2, you should have something like this. You should have 740 times 106 divided by 318. Okay, that's the left side of your problem. And then on the right side of your problem you have 780. This is multiply because I couldn't get the dot. So this is your P2 times your V2 is what you're trying to solve for, divided by your T2 being your 293. So after we do the math over here, the first thing I did is I multiplied these two. I got 78,440, and I still need to divide that by 318. So this is the left side. My dogs are back in here again. Please, guys, stop. And then I have basically 780 times x divided by 293. So in order to get rid of my 293 on the right side of the problem, I have to multiply both sides by 293. This is where we're getting into the really big numbers. Okay, so I went ahead, got rid of 293 on this side, and now I have 22,982,920 on my left side divided by, I'm going to go ahead and get my little pen going here. So remember, this is then divided by the 318, okay? So now on the other side, so I still have, so help me, stupid eraser. Oh my God, my mouse. Wow. Okay, so I went ahead then, and on my left side of my equation, I went ahead and divided the 22,982,920 divided by 318, so that went ahead and gave me the 72,273. But in order, so I still, on this right side, I still had this part. Okay, I went ahead and I got rid of the 293 by multiplying both sides by it, and that's how I got this ginormous number. But now I've got the 780x. So how do I isolate x from the right side? I have to divide both sides by 780. Okay, so divide both sides by 780. So that will get rid of it on the right side. And I have to divide it again on the left side after I'm done dividing the top part by the 318, because we want to get that done with first. Now we have this, whatever this equaled, this problem here gave us this answer, and now I have to divide this answer by the 780, which then is going to give me 92.66 liters. Okay, because I'm trying to solve for the V2, the second volume. Okay, so you will see that problem coming up again. So I want to see that you're working it out, that you're setting them up correctly. I do not expect you to try to multiply and divide all these huge numbers when we do have the calculator. But if you don't set up the problems correctly, you won't get them right anyway. So again, we'll probably have a tutoring session, and I do believe my last line here is my reference. I know I use the study.com Academy that talks about the different, all the different gas laws, and some of it is also in Egan's. Okay, email me with questions.